Hello everyone, and welcome back to The Power of Reason. This is the 7th episode, and specifically the second episode dedicated to understanding some basic principle of statistics, which we'll then be able to apply to how we acquire information and how we make judgments in everyday life. Last time, we have seen the difference between causation and correlation. And today we're looking at the importance of sample size. I would not be considered normal by most if I didn't start this by making a pun and saying that size does matter. And of course, we're talking about statistical sample size, all right? Now that we got that bit out of the way, let's start with the subject matter. First of all, just a quick reminder. What exactly is statistics? In short, statistics is the science of the collection and interpretation of data. Suppose we want to know how many people in the US, or in any country for that matter, currently support the president. We cannot ask everybody individually, so we choose a random sample of the population. The sample must not only be random, but must also be large enough in order to be representative. It could be intuitive that larger samples are more accurate. What is less intuitive is the same fact presented in a different way, which is small samples yield extreme results more often than large samples. What does this all mean? Well, suppose that out there, at this very moment, in the population of a country, 50% of people support the president and 50% do not. So just assume that this is what's happening out there in this very moment. It's a fictitious assumption, but we will make this assumption for the remaining of this example. So 50% of people support the president, but we do not know this and we want to find out. How? Well, by asking some people. There are hundreds of millions of people in the population, so we do not want to ask everybody, because that only happens at the elections. If we choose at random a sample of 1,000 people and we ask them, we find that roughly 50% of people in the sample support the president. We can repeat this again, choosing another 1,000 people at random, and each time we will find that about 50% in the sample support the president. Maybe sometimes a sample will give 49%, maybe another sample 52%, but generally close to 50%. Of course, the sample has to be truly random each time if we want to see this kind of result. So we pick one person here, one person there, and so on. It will be very, very difficult, or I maybe should say rare, to pick 1,000 people at random and find that, say, 90% of them support the president. Because we know that 50% of the population support the president. So it can happen theoretically that, like, by a unique chance, you pick 1,000 people at random and 90% support the president. It can happen theoretically, but it will be extremely rare and almost impossible, like a freak occurrence. Now, suppose we were to choose 5 people at random from the population instead of 1,000. It could happen that by total chance, all 5 people support the president. So we would observe that 100% of people in this small sample support the president, 5 out of 5. But that doesn't mean that 100% of people in the country support the president. It just means that we have chosen a small sample, which is more likely to yield an extreme result. So we cannot use a small sample to make an inference because it would most probably be wrong. Now, let's assume we repeat this poll again with another 5 random people and maybe find that 3 support the president in this group, which is closer to the actual average. Then again, another random 5, and maybe we find that none of them in this random 5 support the president, which is another extreme result. If we repeat this experiment 200 times, we will find that extreme results dilute, and if we average the measurements for all the 200 different 5 people samples, we still get the result that about 50% of the people support the president, like we did for the 1,000 people sample. We can already see that relying on a small sample can yield an incorrect inference, and that increasing sample size obviates this mistake. Simple enough, I think, but let's reinforce this concept in our mind with another example. Suppose we wanted to measure the probability of getting head or tails on a fair coin toss. We want to measure it by doing an experiment. So simply tossing the coin and measuring how many times we get tails and how many times we get head. If we were to toss the coin only 4 times, we could easily get head 3 times and tails once. We would then infer that the probability of getting head is 3 out of 4, or 75%, which is obviously inaccurate. We have to toss it several times, like 100 or 1,000, in order to observe that on average, we will get tail 50% of the times. Increasing the sample size from 4 to 1,000 increases the accuracy of our statistical method. So far, pretty easy, I think, and also sufficiently intuitive. Now, consider an urn containing green and red marbles in equal amounts. Jack, who is a friend of ours, draws 4 marbles at a time. He observes what he got, how many reds and how many green, and then he puts the marbles back in the urn. He takes note only each time that he gets an extreme result. So either all green marbles or all red marbles. Jill, who is another friend of ours, does the same as Jack, but she draws 7 marbles at a time instead of 4. And she notes every time that she observes an extreme result. So either all green or all red marbles. My question is, who is going to see an extreme result more often? Jack or Jill? I think we all intuitively understand that Jack is more likely to see extreme results with his small samples, which is to say, seeing 4 marbles all of the same color is easier than seeing 7 all of the same color. This is intuitive enough. But we do not intuitively know by how much Jack is more likely to see extreme results. If Jack draws 4 marbles at the time and Jill 7 at the time, Jack is actually 8 times more likely to see an extreme result. This can be worked out mathematically. I think this sounds surprising to our intuitive mind, but it's extremely useful to know. And why, you might ask, is knowing this useful? A good and famous example is provided by 2 researchers, Weiner and Zwerling. They considered a study in which the incidence of kidney cancer, which is a rare form of cancer, was measured in all the over 3,000 counties of the US. It was observed that the counties with the lowest incidence of cancer are mostly rural and sparsely populated in the Midwest and South. The first thing one might think in order to explain this observation is that perhaps people in the countryside have less pollution, the air is cleaner, and they eat fresher produce, so they're less prone to cancer. By further inspection of this same study, they then went on to observe that the counties with the highest incidence of kidney cancer are mostly rural and sparsely populated in the Midwest and South. So exactly the same regions. Tongue-in-cheek, one might try to explain this by saying that the poorer counties are where people eat unhealthily, they smoke, drink, and have less access to healthcare. And this is why people in rural counties are more prone to cancer. So which one is true then? The only true explanation is neither of them. The only valid explanation is that rural countries have small populations, which are more likely to show extreme results, which is both high and low incidence of cancer will happen in the rural counties. This is only by the law of small samples, by the way, and that is all there is to know. All other causal explanations are just created intuitively and erroneously because our mind cannot help finding a cause, as we have already seen previously. Our intuitive mind likes to see a cause even when there isn't. We've seen this in the previous episodes. A similar mistake is shown in this other study, also by Weiner and Zerling. One second. So, in a survey of about 600 schools in Pennsylvania, a higher proportion of small schools were among the top performing. This led many charitable foundations to invest millions into creating smaller schools and into splitting large schools into smaller ones. The causal explanation they used to explain why a higher proportion of small schools were among the top performers was that smaller schools can give better attention to pupils. But unfortunately, they were wrong in their inference. The truth is that smaller schools are just smaller samples of students, more variable and more likely to show extremes. In this case, the extremes considered were schools in which most students happen to do well. It is enough to take the average to eliminate this misinterpretation. So, on average, larger schools actually perform better, and this average is the only objective measure that we should use. These experiments show that we must be very careful with interpreting data and statistics because sometimes we can interpret results that are just artifacts due to the method used, and they are not actual results. In this case, the artifact is produced by the sample size, and the wrong inferences arise from neglecting this very fact. But there are other false results that can occur in statistics and in life, most notably the effect of regression to the mean, which is another major concept which we'll look into next time. For now, as always, thank you so much, and until next time, bye-bye.